A reaction coordinate diagram is a very useful tool to help us understand the nature of a chemical reaction. We can understand from the reaction coordinate diagram whether or not a reaction is exothermic, endothermic, what is the activation energy of the system, what is the energy of reaction of the system, and also how much energy is in the activated complex relative to the starting and ending products. So it gives us a basic understanding of the energy profile of a chemical reaction. Here is a representation of a very crude reaction coordinate diagram. Now I don't have anything labeled in here yet, and I don't have you don't understand really what this is about yet until I put some numbers and terms to it. So let's just look at this from a reaction standpoint. Let's say we have a reactant C1, compound 1, plus compound 2 yields compound 3 plus compound 4. So that's my reaction. Compound 1 plus compound 2 gives me compound 3 and compound 4. So there it is right there. There's my products. Here are my reactants. What the diagram says is, remember, this is the reaction coordinate. So this thing here is the progress of the reaction. So on this side we're reactant rich, and on this side we're product rich. And the products are starting here, and then they go through this profile as they go through the reaction that looks like this. So let's label where the products and the reactants are. So we're going to put C1 and C2 are here. Those are the reactants. And then C3 and C4 are here. Those are C4. And so these are our products. I'm just going to put product and react. Okay? So products and reactants, and that's where they're located on the diagram. So the energy associated with the reactants is this energy right here. Whatever this energy turns out to be on our diagram, on our scale here. Here's our potential energy scale. So this would be 0, and then whatever this value is here, it would be the potential energy of the compounds 1 and 2. And you can think about it as these are the stored energy in the chemical bonds of compound 1 and compound 2. Now, if we go over to products, compound 3 and compound 4, that's this energy level here, and we could trace that all the way back to here. So let's just put a little mark here. And whatever that value is, that numeric value and unit is there, that's going to be the potential energy associated with the products. So that'll be the potential energy stored in compounds 3 bonds and compounds 4 bonds, and that dimension right here is D, right? And the reactant one is going to be this one here, A. So A is our this is our PE of our reactants, and I'm just going to put react. And D is our PE of our products. All right. So you should understand that is a critical term. So here's our energy for our represents the energy for our reactants. It's this value right here, and this is our energy for our products, and that would be this energy value right here. Right. Now notice we have some other things here that we have to understand what they are. So we have a letter B, and let me just redraw that letter B over on this side so we can put some label to it. Let's just put B here. It's the same thing as on the other side. I just moved it over to the other side of the curve. Now letter B represents this energy change as we go from here to this top of this curve here, and I'll tell you what that top of that curve is in a minute. So that's the energy associated with just this distance here. Okay. Now, when we make a reaction or do a reaction, there's a point at which when we mix A and B, or excuse me, compound 1 and compound 2, we start breaking the bonds in compound 1 and 2 and start at the same time forming the bonds in compounds 3 and 4. So you could draw what this thing looks like over here, and then this imaginary or this pseudo reaction complex. In other words, there are bonds being broken and formed in compounds 1, 2, 3, and 4 all at the same time. So the compounds here are starting to form bonds from breaking bonds in compounds 1 and 2. So here's compound 1. We break those bonds and form compounds 3 and 4 bonds. Compound 2 is breaking bonds and and with the bonds being broken, or with the atoms being separated in compounds 1 and compounds 2, they're going to be starting to make new bonds with the atoms in compounds 3 and 4. So we call this whole thing here a reaction complex, and that is located right here. All right, so that's my reaction complex. And that energy, and we're going to draw a new line here. That energy, we're gonna draw this line here. We're just going to go through C, but you realize it's going to be that we'll call that letter E. Letter E is the potential energy. So E equals the potential energy of the activated complex. Right, activated complex. And that is the maximum energy that you're going to see in the system at any one time. So we put all this energy in here. We've put all this energy into here. We've now achieved this state where we have bonds being totally broken. Then new ones are just starting to form. And when the new ones start to form, remember, they release energy until they get to the final state of where the final compound or compounds are located. So here. So E right here, this dimension is the maximum energy associated with breaking all the bonds in compounds, in this case 1 and 2, and then you just start to form the compounds 3 and 4. So E will be the sum of the potential energy in the reactants plus the activation energy. All right. Now let me erase some of this stuff so we can get one more thing in here. Let's erase some of this. And you can always go back and look at this if you need to. So the other things that we want to make sure as we understand is, what is this letter C represent here? Now the letter C represents, here's my C right here. C represents the energy associated with the heat of reaction. So let's see what that is right quick here. Suppose we say now that we've gotten rid of our thing here, that this thing right here is 100 joules. Actually, let's make it 100 kilojoules. So let's make it 100 kilojoules. 100 kilojoules, and we said that that was the energy associated with the reactants. So it's 100 kilojoules. And then let's say this top thing here is 200 kilojoules. That's this one right here. And the bottom one here, we're going to call that, let's just call that 25 kilojoules. Okay, so now we can do these things to calculate some energies here. So we know that from what we said before, that the 25 is going to represent this one right here, right? And that's also our energy of our products. And then the 100 kilojoules is going to represent this, and that's going to be the energy of our reactants. So when we add them together, we can figure out, now we can use these two numbers to get the heat of reaction. And remember, the heat of reaction is a very simple formula. It's delta H equals H of the products, that's the energy of the products, minus H of the reactants. Okay, so H of the products minus H of the reactants. So let's put in the numbers here now. So remember, This is our 25. That's going to be our heat of our products. So let's put that in real quick. So we're going to put in delta H equals 25 kilojoules. And then from that, we're going to subtract our heat of reactants, which is this number right here, this number here. And so we have to put in 100 kilojoules. And when we do the math, we can see that it's minus 75 kilojoules. Right? Now, minus 75 kilojoules is the heat of reaction, delta H of the reaction. And you can understand why it's minus, because we're starting with a higher number here. Yes, we do over this little hump, and we'll talk about that in a minute. But we end up at this plateau here. We start at this plateau here of 100. And then we drop down to 25. So we're losing 75 kilojoules. And it's not like it's negative heat. There's no such thing as negative heat. Recall that when we have negative heat, it just means that the system is losing the heat, right? It's being absorbed by someplace else, but the system, the chemical reaction, is losing the heat. It's being given away, right? If it was being absorbed, it would be positive. Okay, so there's one more thing that we have to understand is, and that is this part of the curve right here, this hump here, right? What is happening at this point of the curve, right? So we're starting out at 100 kilojoules, and then all of a sudden we're at 200 kilojoules, and then we're back down to 25 kilojoules. So what is happening here? Well, let's just draw another line in, right? We're going to draw this line here, and now this line is going to be called D, and it's going to go all the way to the top and then all the way to the bottom. We're going to call that E, and we're going to erase some of this other material here. So let's just... Okay, so we erase some of the material. Now let's see what E is. E represents the energy of the activated complex. E equals the potential energy, when you write that PE, of the activated complex. And what you might want to ask, what is the activated complex? Recall that when we do a reaction, we are going to have to break the bonds in compounds 1 and 2 here, and then form the new bonds here. Well, these bonds just don't automatically break, and then these things just hang out, and then we form new ones. They form this activated complex where we're starting to break the bonds in compound 1 at the same time where the atoms in compound 1 and compound 2 are rearranging to form the new compounds of compound 3 and 4. So as we break bonds, the atoms rearrange themselves in so this one giant complex here, and that complex has this maximum energy here. And the complex is actually what is located as far as species-wise at the top of the peak here. Right? Now, the other thing that we have to understand is, so that's the total energy of this activated complex. So what else do we have to understand here? The last thing we have to understand here is this dimension here, B, where we're starting out at 100 kilojoules for the reactants, and then we're going up to the energy for this reactive complex. Now remember, this reactive complex, as we add energy, we start to make the bonds vibrate more, start breaking down, dissociate a little bit, until they're just starting to break and form into new bonds, but we've had to add energy to do that. And the energy that we've added is this distance here. So it's 200 minus 100. So the energy that we've added is the activation energy, and in this case it's 100 kilojoules. So B is my activation energy. Activation energy. And it's basically E minus A. So if you want to get that, it's this energy here, this total energy of the complex minus the energy that we started with the reactants. So E minus A gives me B, because if you add the height of A and the height of B together, we get the height of E. So the activation energy is just this portion of the curve. All right. One more thing about this curve is that if you look at this curve, you now know that it's exothermic, because the energy of the reactants here is higher than the energy of the products. Right? If the energy of the reactants is higher than the energy of the products, we're giving away energy, and therefore it's exothermic. Now on this slide, I've given you two reaction coordinate curves with less of the A, B, C, D, but I've also talked to you now about showing you which one of these represents an endothermic reaction. And an endothermic is we have to add energy. We are adding energy to the system, and therefore the energy of the products is greater than the energy of the reactants. And I'm talking about potential energy. The reactants. Right? The potential energy, P energy, the potential energy of the products is greater than the reactants. And you can see that right here, right? This energy level here is higher than this energy level here. So we've added all this energy to get to the complex, then we've only recovered some of it. So the delta H is here. And delta H, therefore, delta H, for this reaction, delta H is positive. All right, the products have more energy than the reactants, and we do products minus reactants, and the delta H is always going to be positive. And on this curve down on the bottom here, this is an exothermic curve. Again, it looks very similar in shape, except now we're getting energy, so we get energy. We don't have to add it. We do have to add it and to get the activation energy, but we recover all that and actually get more energy out than we put in. And so therefore the H of the products is less than the H of the reactants. And that difference is going to be, that difference equals a heat of reaction, right? And that difference is going to be equal to the energy of the reaction, and therefore delta H is going to equal a negative value. So when delta H is negative, it means that the reaction is giving us energy back. Right? We have more, it's more energy back. And when delta H is positive, we need to add additional energy to make it work. Right? And in this case, when we say negative energy, there's no such thing as negative energy. All right, let's just write that down. Negative energy doesn't really exist. There's no such thing as negative energy. Negative energy just means that we're getting material back. So the sign here, this sign here, when it's negative means that we get the energy. We don't have to add energy. So plus means we're adding energy, and negative means we're getting energy. So again, you can see that on, here's my exothermic curve, right? Here's my reactants. Here's my active energy, and it's very small because I'm starting out much higher with potential energy for the reactants. I don't have to add that much energy. But once I do add that energy, I get all this energy back, and my delta H here, again, is the difference in the energy level of the products minus the energy level of the reactants. So one more thing about a reaction with respect to the reaction coordinate diagram. We can show you on the reaction coordinate diagram that what happens when we add a catalyst to a chemical reaction. Now recall that a catalyst is going to make the reaction easier to go. And how it does that is it changes the activation energy of the reaction. So let's see how that works. In this case here, this is our coordinate diagram. Now we haven't put our axis here. This would be potential energy. When we do this, we see here that our reactance has this potential energy right here, and that's represented by delta, this energy right here. Right? If this was 0, this is energy right here. The uncatalyzed reaction needs this much of an activation energy to go from where we are with our reactants at this energy level all the way up to the activated complex. So here's our activation energy. When we add a catalyst, we reduce the activation energy, so we only need this much right here, represented by here, activation energy of the catalyst. Notice that it's much lower. Notice what also happens is we don't affect the potential energy of our starting reactant, and we don't affect the potential energy of our products. They do not move. The only thing that changes is how much energy we need to add to get over the barrier to drive the reaction. In this case, we have to add a lot of energy to get this to work, and in this case, when we catalyze it, we don't. We have to add much less. The other thing too is, remember that the forward reaction from reactant to product, we only have to add this much to go, and so the activation energy is lower for the forward reaction. It is also lower for the reverse reaction. So we start with products. Let's say this is equilibrium. When we start in products and go backwards to reactants, so basically what happens is the products would become the reactant, and then the reactants become the products. It also is lower in energy to do that reverse one. So it affects it equally. Both the forward and reverse reactions are equally affected by adding a catalyst. We don't add a catalyst, we need a lot more energy to get this to go this way or this way. Adding the catalyst lowers the activation energy for both directions.